So welcome, thank you for coming to my talk. Today I want to talk about open source library QuickStreams, which introducing in the version 2 a new way how to process data, streaming data in Python. I want to talk about the kind of market in stream processing, motivation why to use it, and then at the end show you a bit how the library works in action by building a real-time heat map. So think of it like you have a BBC or Guardian and they just put a new article on a website and they want to see how people looking at the homepage. So I'm Tomáš Neubauer, I'm CTO and co-founder of Quix, and let me just give you a very short kind of history why I'm building this library with my team. So we have met co-founders in F1 racing, and I was leading a team that was connecting F1 cars to the cloud. So people, all different engineers from mechanical engineering, data engineering, ML engineering, can build a real-time decision insights what to do with the car next time it comes to the pit. And sometimes literally a second great decisions. And because the amount of data was humongous, it was around 30 million different numerical values from different sensors every minute, we were kind of forced to opt for stream processing and use Kafka, etc. And this is where I kind of first time by myself realized how difficult is this stack to be used from Python, because it's all coming from Java and JVM ecosystem. And it was really difficult to enable all these cross-functional teams to build these real-time pipelines. So this is where we had decided to quit and build this company. So just to understand my audience, can I ask you who ever worked at home or professional project with Kafka before? Oh, that's quite a lot, okay. Well, these slides probably should be disabled, but who using Pandas or any similar library? All right, cool. That is going to be important in a second. So what is the stream processing? What is the motivation? And when you should use it? Because this is quite important, because if you don't have a reason to use it, you probably shouldn't, except maybe to increase your salary in the future, but apart of that, really no reason. So you either have to have a lots of data, which would be costly or even impossible, which was our case, to land in a database in a raw format. So we basically couldn't land the 30 million values per car to the database and query it at the same time. So the traditional dump data to database and then analyze it didn't work. So then what you can do is normalize data, join data from different sources, downsample data with stream processing. Maybe you don't need the raw frequency of your data in the database, and filter it, and then land it in a format that your particular database likes it. In our case, it was InfluxDB and Mongo. We had basically two syncs in our pipeline, each syncing different data, because there was not single database solving time series data and metadata at the same time. And the second use case is when you need to react to data fast. So that could be any sort of alerting, event detection, anomaly detection, or just real-time application like Uber. You know, you're trying to connect the driver and the passenger, and that has to all happen in real time. Now, if you put the check on both problems, then that is super great, but even one of them is a reason to go to stream processing. And then when you get to this journey of building stream processing pipelines, then you have basically two options. One is to use some broker, that could be Kafka, Pulsar, or something from cloud providers, and then use the client libraries for that brokers and build it by yourself. The second option is to opt for full-fledged server-side stream processing framework like Flink or Spark Streaming. Now the first option is elegant, lightweight. You have usually a well-supported client libraries for all different languages, like Python as well. And you don't drag any JVM dependency to your code. The broker might be written in JVM, but your code doesn't have to be. And that's actually quite good, although you have to still solve your deployment and your Kubernetes and your CI/CD pipelines, all of that. But it's doable. Up to the moment when you have to move from stateless processing to stateful processing. So when you process your data only message by message, and at that moment you don't care about previous messages. So think like a fraudulent transaction detection, when you really care about just the person and the transaction and not what transaction did before, then it's okay. But the moment you want to build something stateful, so that could be our today example where we're gonna aggregate heat map of people moving around the website for 5 minutes, or you just want to look at the previous transactions of that user or customer. That moment it gets very, very difficult. And I would not recommend going that journey for just one project. It's really not worth it. So at that moment, you might be tempted to go to something like Apache Flink. But the problem with the Flink and Spark streaming and similar engines is that they are as well built in Java. And because the way how this works is that there is an engine that makes sure that the data, state, and code get redistributed in the engine, you actually not writing your code that runs in your IDE, but you're just instructing this engine to do the job. And as a result, even though these engines have Python wrappers, it's just a thin veneer of Python on top of JVM code. Because everything cannot run at the end in a Java-based Flink. So as a result, there are a couple of disadvantages with these frameworks, but they solve the stateful processing very well. They are 10 years old and they have lots of features. So the first problem is debugging. See that the pictures not always work. So the debugging is something that I guess every developer wants to have. You can say it's a table stake, but you will not get this with the server-side approach, because the code is not running in your laptop, in your IDE, it's running in your engine. So here, if you use a library approach, which is the first option, then you can go line by line and see what's going on. The second problem is the dependencies. If you're connecting your code using the option 1 to any sort of source or sink of your pipeline, let's imagine MQTT broker, Kafka, or you're syncing data to S3, to databases like Influx, then you're using the client libraries of these technologies and client libraries of your broker. So you're kind of connecting two very well supported, very easy to use libraries in your language of choice together. Not the case with server-side engines. So if you want to connect Flink to Kafka, well, you're going to have to import a jar file of Kafka Flink connector, and then you're going to have to import the jar file that this Kafka connector depends on, which is Kafka client library. They both have to be in the right version between your Flink, your Kafka, and your connector. And if you do anything wrong, then you will get a Java exception. So that's basically the developer experience if you're trying to do that. Now, if you don't find a connector that you want, well, then you are on your own to build a Flink connector in their framework. And the last bit I just want to mention quickly is the UDFs. So basically, the way how you're going to do this, if you're going to use something like PyFlink, is that you're going to build your Python UDFs. But the way how it works, that they have a Java runtime, and then you have a Python runtime. It's connected to a socket connection. And now, not mentioning that if your payload for this method is big, there will be some performance implication. But if anything gets wrong, then debugging that problem gets very difficult. So, is there a third way? So what I want to show you today is something in the middle. It is the option 1 plus a stream processing library that solves all of that stream processing drudgery that you would have to do by yourself. So how it works. So when you're doing that by yourself, what you're basically gonna do in your code for your project is you would get the data, you will split it to streams based on some key. So you partition your data. Then you would deserialize it with some deserialization. Then you would basically make sense of time series data to some level. And then you would maintain the state in memory. And then with some checkpointing, you will save it to some database. And then you would send the output to a different topic. And then you would make sure that you're committing correctly the input topic and your changelog topic. It's lots of work. And basically what we have done is we have taken all of that and we have packaged it behind a familiar API, which is Pandas API. So the idea here is that you control your data like they would be static, but they are not. So imagine you load the data from CSV. You have 100 lines in that CSV into Jupyter Notebook, into Pandas. Then if you add a new column, which just adds two other columns together, well, you will do that for all rows in one operation, job done. If you do that in quick streams, basically what's happening is that every time you get a new row in a topic, you would do the operation immediately and send the result to the output. So you can think of it as something is happening with the... yeah, good. So what's going to happen is that every message is kind of a virtual row in your virtual table. And it's just happening continuously. So these 100 lines will not be done in once, but as your data flowing in, they will be processed real time. And that's how it all works. And technology-wise, we basically had to solve all these 4 problems. It has to scale, it has to be reliable, so if there's any sort of hardware issues, you restart your service or whatever, your state has to be intact, so you don't want to lose it. And it has to be correct. So let's say that you're gonna process your transactions and you're gonna keep the balance. Well, if you accumulate transaction twice, somebody's not gonna be happy. And the 4th is extensible. You need to make sure that you can use the Python ecosystem at fullest. So all the ML, AI, mathematical, statistical stuff in a pip is at your disposal. So we do that by combining Kubernetes, Kafka, and the stream processing library all together, and using replica system, redundancy in Kafka and Kubernetes all together, plus with some tricks like changelog topics to do all of that without introducing the engine. And this is how it works. So today, we're gonna get in one topic where people are with their mouse. We're gonna receive that in our stream processing service. We're gonna do a rolling window, and then we're gonna output just a sum of people in that bit of the screen in the last 5 minutes. And just quickly, this is how it then scales in Kubernetes. And you don't have to care about it. We would do that. But basically, the way how it's going to scale is that each stream, each page in your website, in our case, is going to be one stream, and then you just horizontally scale compute, which is replicas in the Kubernetes, and you horizontally scale your Kafka topic with partitions. So let's do it. So first, we're going to get a browser application, which is going to send through the WebSocket gateway this data, and we're going to calculate the heat map. So here I have this project, and I have built the environment talk. So this is you looking at the Quix cloud, which will just let you deploy these pipelines. And here I have the pipeline from start. Do you need to hold the mic? No, it's fine. I'm used to this. So this is a pipeline where we have a source, which is a WebSocket service. Then we have group by, and then we have the heat map aggregation and the WebSocket output. So if I now open this website, and I open the source, and I just move it like this, and I'm going to start to move around here. Now you can see that we're creating a heat around the demo. If I move here, now we're suddenly moving the heat to a different part of the page. Now if we would wait 5 minutes, the demo will start to disappear, and as the new users come to this page, you will get this information. So let's now build this together from scratch. So I will stop this, and here I will stop this heat map aggregator. And we're going to do a hard bypass. So basically we're going to create a new service around this. It's going to do the same. So here I'm going to create a new transformation. I'm going to use this template. And I'm going to call this a heat map stage. Okay. Now this is going to give me a microservice which is prepared to run in this pipeline, including Docker image, Helm chart, all the dependencies. I'm just going to run it. And I'm just going to tell it that I want to listen to a topic which is already partitioned, and I want to output it to heat map. Great. So now if I go back to my pipeline, we have a new service which is ready to take the job. Now, we have bind this environment talk to a branch talk, which means if I go to my Git Kraken and I just pull all the changes, I will get this locally. And now I go to my Visual Studio Code and open a new terminal. And there's a quick CLI which helps you connect this code to your cloud infrastructure. Of course, you can run it against local broker, but now I'm just going to use my environment there. So I'm just going to do quicks, use, and there's a heat map project, and talk. Cool. And then I will go to cd heat map stage. And then I'm just going to I'm going to synchronize the variables for this service so I can just run it now. So if I go back to this service, and I'm just going to, for now, comment out the output because we don't have the output yet, and print it, run it, it's going to give me the data. There we are. Amazing. So now we have the data in a Python code, and now it's our job to make the actual heat map. And if I can just now ask you if you can hold my microphone, it would help. Because now it's going to be a bit of coding.
Of course.
Great. So now, the first thing I'm going to do, and this is how Kafka is kind of useful for this, I will make sure that every time I run this, I will get the data from the start. Because there's a temporary persistence for the data that has been sent. Great. And now, first thing I'm going to need is check what I'm actually getting. So here I can explore the data. Great. So we're getting some information about the session, not important, but we're getting the size of the page and mouse coordinates. Well, let's use that. So I'm going to copy this column. And as you are kind of used to in Pandas, I'm just going to do this. Let's run it again. Great. So we have now this information. That's enough for now. So let's first calculate a relative position of the mouse to the screen, because everybody has a different screen size. So then, what I'm just going to do here is SDF, and think of SDF as a streaming data frame, so it's like a DF. And I will say relative x is equal, no, that was the wrong one, mouse coordinate x divided by SDF window, and there's going to be width. Great. And then we're going to do the same for the epsilon. Now, this should give us just 2 columns. If I just filter this projection to this, and it should be almost there. It's a bit slower on this Wi-Fi, but there we are. So now we know relatively to the page where our people are on our page. So now we just have to split it to tiles. Okay? Now what's happening now is this is stateless operation still. The moment you move your mouse, that moment this will process this calculation and would output this result. So it looks like it's static, but it's not. And if I stop this now, I'm just gonna do last operation before we get to stateful stuff. So I will say let's divide it by 10. So grid size 10. And then I will do here lambda row. So this is where lambda row. And then we're gonna return 2 properties. The tile x and tile epsilon. Now we need to use the math because we're gonna need to create integers, not doubles. So here we're gonna do math ceil, and then this column multiplied by the grid size. Cool. Now we're gonna do the same for another dimension, and we are almost in a business. Cool. So now we would have just information you are in a 5 and 4 and a grid. There we are. Amazing. So the last bit we have to do to make that heat map working is just aggregate how many people were in each coordinate, in each tile on a screen in the last 5 minutes. And this is when the things get super tricky if you would do this without the stream processing library. So here I will just do SDF equal SDF hopping window, and let's get like 1 minute for now. And then how often I want to emit this window, 4 times per second, and I want to wait 500 milliseconds, half of the second, for some slow data. Maybe somebody had a slow internet. And then I'm gonna create the heat map function where I'm gonna accumulate that. And what basically this is doing is calling this function every time I get the new information, and just it's my responsibility to aggregate, to reduce the new information with the state in that window. But everything else is done under the hood. So here I would get an x coordinate, and I will get it in string because dictionaries don't like numbers. And so I will get the row tile x, and the same for epsilon. And then the way how I'm sending it to front end is just a dictionary of dictionaries, when first level is x and the second level is epsilon. So basically if x is not in the state, I would create the new thing there. And if epsilon is not in state x, then I would create the new record there with 0. And then, when I have this created, I'm just going to do basically this. And return it. And we should be done. So let's just thank you. Let's just summarize what we have done here. So every time we get a new row, we just put +1 to that grid coordinate in a state, which means that at the end, if I run this, yeah, I have to here just call it. So I would reduce the heat map, and I would also initialize it with the empty state when I need to at the beginning. There we are. Cool. And because we are not interested in any information before we end the window, I will just do the final. So now the last thing I'm going to do, because we don't want to really here wait for changelog topics, I will disable the changelog topics. So they basically backed the state for you as well. Oh la la, so it works. So let's just look at for a moment here what we have. So we have the value, and in an x3 and epsilon 5, we had one person in the last 5 minutes, or in our case, 1 minute. And basically, this is how you build such a pipelines with quick streams. Now, obviously, what I can do is just put a breakpoint here and just stop this and run a debugger. And if I do that, if I would have any problem in this function, I would just debug it, as I'm used to with the normal Python. So the moment I get first row, well, I just go line by line and check the row, check my state, get it done. And so from this moment, then I just go to my pipeline here and deploy the application, and I'm done. And this is in my environment. I can create pull requests to merge it to production. So hopefully it made sense, and you can give it a try. It's open source, and it's on GitHub. It's in a pip. You can use it with your broker. You can use our cloud as well if you want to create these pipelines. It's really up to you. And if you have any questions, well, I'm here. Thank you very much for coming here.
Yeah, I think there was a question about, is it free? But you already mentioned this is open source.
It's open source.
How does the performance compare to something like Flink, especially for high volume streams?
Yeah, so the performance, when you use the Python UDFs in Flink, is actually comparable, because at the end, the data has to go to the UDF, and there's no interaction between any runtimes in quick streams. So if you're using PyFlink and you're using its purpose, which is Python UDFs, the performance is comparable.
Okay, thank you so much. So big applause to Tomáš for this great presentation.